Okay, so last time we talked about the how to calculate the potential generated by a line of charge. So this time we calculate another case. So this one is potential due to a continuous charge distribution with a charge disk. Okay, so yeah, this charge disk you have seen it in chapter 22, chapter 23. We try to calculate the E field generated by this stuff. And for this circular disk, we can only calculate the E field in the central axis. And later on, we try to assume that this circular disk is infinitely large. Okay, so that it will generate a uniform E field on both sides. Okay, so this time we try to calculate the potential generated by this disk also on this axis. So okay, so here we try to separate this disk into many rings with different radius, just as what we did in chapter 22. Okay, so here we have a dq equals sigma. Okay, this is a small letter of sigma, and then times this 2 pi r times dr. Okay, what does it mean? So actually, this is a surface charge density， 就是面电荷密度。那 okay, so which means that originally it is like dq equals sigma times dA. Okay, so we already assume that this surface charge density is uniform over the whole disk. So we can use this dq equals sigma times the dA. Okay, so what is the dA? dA here we have the ring. Okay, so of course this is very thin, but we need to calculate its area. Okay, so the area is like we try to use a scissors to cut it and then try to flatten it. Okay, 就是把它剪断它是一个圆环，把它剪断，然后把它铺平 ，flatten it. So it turns out to be a rectangle. Okay, why? I don't know why, but yeah, you assume it turns out to be a rectangle. Okay, so the height here will be this dr prime. Okay, this dr prime with the height of this dr prime will be the height of this rectangle. Okay, so the width will be the circumference of this circle. Okay, 就是那个圆周。Okay, so it turned out to be 2 pi r prime. Okay, 2 pi times the radius will be the circumference. So the area will be the width times the height. So it will be 2 pi r prime times dr prime. Okay, so this is the area of this ring. Okay, so here we try to plug in this thing into here. So we have dq equals sigma times 2 pi r prime dr prime, something like this. Okay, so here we have a dq, so we can make use of this formula. Okay, originally we don't have this d here, but after considering this small part, so we have a dv generated by this ring, and then we try to we can have all the expression for different rings with different radius. So we have dv equals this k times dq is this dq, and then over r. Actually, this r is referring to the radius of this ring. This capital R means the radius of the disk. Okay, so this, which means this small r is actually between 0 and capital R. So you swap the r from 0 to r, capital R, so that it will combine together to be a full disk. Okay, so this is the dv, and then we have dq with this expression, so we can plug this expression to here. So we have k, and then this is the dA from here, and then the ow, okay. Sorry, the ow is not there. The ow should be here. The ow should be here. Okay, so because we are concerning the potential at this point. Okay, so the ow should be the distance from the ring to this point. Okay, so this is the ow, and this one should be the capital R prime. This one should be the capital R prime. So using the Pythagorean theorem, R is the square root of a capital R prime square plus C square. Okay, so here should have a prime here. Okay, should have a prime here. Okay, we don't distinct. We should differentiate this one with the full radius. Okay, so this one should be R prime. Should be capital R prime. Okay, so here we have the expression of dv, okay, in terms of R prime. So we have a dr prime here, and then we also have R prime here. So all the other variables are independent to dr prime. So we are ready to integrate this stuff. Okay, so we have a v equals integration of dv. And of course, the integration is from 0 to this one should be R. This one should be R. Okay, so we plug this stuff to here, to here, and before doing that, we can have some cancellation. Okay, we can actually cancel this pi with this pi, these two pi with this 4. And this is pretty much it. So we have a sigma 2 epsilon naught here. Okay, so it goes to here, and then R prime dr prime go to here, and then these square roots go to here. Okay, and here we also have this. We also have this prime. Okay, so this thing is easier to integrate than the previous integral in the previous lecture. Okay, so in the previous lecture we don't have this R prime here, so that we need to assume we need to use some substitution with the trigonometry function, with the tangent function. So the calculation is more complicated. But here we can use the chain rule. Actually, the chain rule. So this R prime dr prime. Okay. So this R prime dr prime will become dr prime square plus R prime square plus C square. C square is actually a constant. So yeah. So it doesn't really matter. So we have a this stuff to be R prime dr prime. Okay. So substituting this one with this expression, we have a sigma over 2 epsilon naught integration of from 0 to capital R, and then dr prime square plus C square, and then square root of a C square plus R prime square. Okay, so this stuff and this stuff is the same. So yeah, so we can regard it as another variable, or if you are familiar with it enough, so you don't need to really substitute it. So this one is actually the polynomial function. Yeah, with this big variable to the negative 1/2 power. So the integration of it will become this stuff to the 1/2 power, which is the square root of this thing. Okay, the square root of this thing, and then evaluate from 0 to R. Okay, 0 to R. Okay, of course, which means that R prime to be 0, R prime to be capital R. Okay, so if R prime to be capital R, so it becomes Z squared plus R squared. And then take the square root, become the first term. And then if you substitute R prime to be 0, so it turns out to be square root of Z squared, which is Z itself. Okay, so the integration of this thing turns out to be the two terms in the parenthesis, and then this constant just go to here. Okay, and then this is actually the solution, the closed form expression of this potential along this z-axis, So note that the variable in the second integral is R prime and not z. Okay, so because if you are not familiar with the integration, then when you just look at the integration, you sometimes you may be confused or which variable to integrate, but actually this is the R prime, and even after this substitution, R prime and z are all in here, but actually z doesn't change at all. Throughout the integration process, because if you just look at the graph, okay, with the range to be different, the z doesn't change at all because the p is fixing here. Okay, the z doesn't change, so the only changing variable is the R prime in the integration side. So this is what you need to pay attention to when you doing the integration with multiple variable there. Okay, you need to be careful which variable is variable. Which variable? I mean which variable can take different values. Which variable is a fixed? Is a constant. Okay, so this is the expression of this potential at point P. Okay, so here we talk about calculating the field from the potential. Okay, so so here we talk about so suppose that a positive test charge Q0 move through a displacement ds from one equipotential surface to the adjacent surface. The work of the electric field does on the test charge during the move is this thing. Okay, so this is the definition at the very beginning in this chapter. So W equals this negative Q times the potential difference. Okay, and so this is a general case. So suppose that we have a varying potential or potential field. Okay, so in that case we have some equipotential surface indicated by these orange dotted lines. Okay, so here we have a test charge starting at this point and then moving along this this path. Okay, so this on this figure, of course, this path is a straight line, but in the practical case, the path doesn't necessarily to be a straight line; can be a curved line. Okay, so it doesn't really matter, just for demonstration. But here we also try to separate this path into many small segments, so that for each small segment we at least can regard it as a straight line. So for this ds, okay, and at this point we assume that we have a E field. Okay, I've mentioned last time, I think, the E field at that point should be perpendicular to the equipotential surface. Okay, so at this point the E field line, we assume it pointing to the top right direction. Okay, so this is the, and actually this is the work done. If we considering the E field, if we consider E field or the potential, so on the other hand, we can also consider the work done in a mechanical sense. Okay, so f dot ds is another sense in the mechanics point of view. So the work done is f dot ds. Okay, so f dot ds will be q0 times e, q0 times e, because we have an e field here, and this is the positive test charge. So this f should also point to the same direction. So f equals q0 times e is acting on this charge at this point. So we have a qe dot ds to be the work done. Okay, so these two work done should be the same thing. So we put this thing here and then we put this thing here. So this is a dot product, so we have a e times ds, and then we should also multiply by the cosine of theta, and theta is the angle between the e field and the ds. Okay, so here we have a cosine theta. So in such a way, we can do some cancellation. Yeah, so this q0, the test charge usually will cancel itself. So we just remain this e times cosine theta on one side, and then we move this ds to the left side. Okay, so it turns out to be negative dv over ds, and then we swapping left and right, so that it becomes e times cosine of theta equals negative dv ds. The derivative of the potential with respect to the displacement. Okay, and then take the negative sign, will become this e cosine of theta. So e cosine of theta means the component along this s-axis. Okay, so for x-axis component we write it as ex, for y-axis component we write it as ey. So for s-axis component we write it as es. Okay, so here we try to write it as es. Okay, es equals negative dv ds. Okay, becomes this formula. Okay, so we have this formula, and actually, what we are familiar with is the Cartesian coordinate. The Cartesian coordinate 就是直角坐标系. So in that sense, if it is in a Cartesian coordinate, we can actually write it as three independent equations. So it is so they are ex equals negative dv dx, ey equals negative dv dy, ez equals negative dv dz. Okay, so you just need to repeat it several times. Okay, so yeah, so maybe we yeah. So so in this case, it doesn't necessarily this yeah, but I mean this is not the path of itself. It already separate the path into small segments. Okay, so it doesn't just show the whole path. Okay, so 我的意思是我刚才说这个是这个路径，其实这个不是路径嘛，就是这个整个路径它没有画出来，它已经把这个路径已经切分，它只是画其中一部分而已。那一部分的话，对应就是这个 ds 这个轴。那如果你要得到 ex、ey、ez 的话，那就是把这个动作重复做几次，只是说把这个 s 换成 x、y、z 而已，那你就会得到同样的这几个式子。Okay, so we can actually obtain these three equations by repeating this procedure, just by swapping, replacing s by x, y, and z. What? Okay, so yeah, so actually if we need to write this thing in three equations, so that will be quite trouble. Okay, so in the mathematics, okay, so the physician or the mathematicians, so they usually are lazy to write 3 equations if they are quite repeated. So they use a symbol to write these 3 equations together in just 1 equation. So it turns out these 3 turns out to be this equation. So as much as Ex, Ey, Ez are the XYZ component of a E field, so this, if we know all these 3 E field, okay, E fields, then we actually know the E field vector, okay, the whole vector. And okay, so but the right side we have a derivative for the potential in different direction. Okay, so actually this derivative in high dimension becomes this upside down triangle. They don't try to use the normal triangle because delta means the difference. Okay, so here they use a upside down triangle to represent this is the derivative in multi-dimension. Okay, and actually this one we call it an operator， 就是一个运算的运算符或者是一个运算一个 operation generally operation 就是加法、减法、乘法什么都是一个 operation， 求导数也是一个 operation。那这个 operation 就更或者 operator 就更复杂一些，它叫做 gradient 中文叫做梯度梯度。那最近几年的话 ，AI 就很流行嘛。那 gradient 的话，其实是怎么说？就是神经网络或者神经网络理论里面的一个核心，它叫做 gradient descent， 就是梯度下降。它用来作为那个训练模型的一种算法了。所以这个梯度的话其实很多领域都会用到，但是最近如果是训练神经网络的话，其实是它是一个怎么说，就是它这个理论里面的一个核心的部分，基本上所有的训练方式不是所有的，大部分很大一个系统的训练方式，它虽然有改变，但是其实也是基于这个梯度下降gradient descent 不过 gradient descent 就跟这个无关，这个 gradient 就是这个倒三角符号。Okay, so actually, previously we have learned this. Okay, we have learned this as the definition of the potential. So the potential is the negative of E dot ds integration from the starting point of the path to the final point of the path. Okay, so this is the integration. So you can consider it's an integration of E. Okay, you don't care about it is a single integration or a line integration. Okay, so simply speaking, it's the integration of E becomes the potential. So you can also imagine that the derivative, although it is not the derivative. Okay, so it is like the derivative of the V will be the E field. Of course, we have the negative sign here. Okay, but yeah, what I want to mention is that the integration of E field is related to the potential, and the derivative in quotation is related to the E field. Okay. So actually this one I suppose you should have learned it in the calculus class, although not this version. It should be the single variable version, like when you learn the derivative, it is like dy dx. Dy dx should be like y of x plus delta x. Sorry, should be like limit x. Y of x plus delta x minus y over delta x. Okay, delta x tends to 0. Okay, so this is a definition of the derivative in a single dimension. And then if you need to take the integration, it will be like integration of f of x dx from a to b, okay, becomes another function f of x. Okay, but at the beginning, this integration should be like a Riemann sum. Okay, should be like a Riemann sum. Okay, I don't try to write it out fully, but the definition of the integration and the derivative are totally two different things. But finally, it tells you that the integration, you can just use the antiderivative to make the integration easier. You don't need to go through the Riemann sum every time, and probably you don't go through for even once. But the idea is that why these two independent definition is the reverse to each other. So in the calculus class, the professors tell you that there's something called the fundamental theorem of calculus. Fundamental theorem of calculus 就是叫做微积分的基本定理。基本定理就是告诉你说导数跟积分或者是定积分这两个完全不同定义的东西，它们其实是逆运算你可以在不定积分拿这个反导数拿进来，然后去带这个向下线，你就不需要去做那个黎曼河。OK， 那这个的话就是 Fundamental Theorem of Calculus for Line Integrals， 当然有其他的版本，不同的维度。这个是高一个维度的，也有再更高维度的，2维到3维的。之后会提到一个叫做告斯定理的它不是告斯定律不过后面32章的时候我会补充那个告斯定律跟另外一个叫做 Stokes Theorem 一个叫做 Stokes 一个叫做 Stokes Theorem 一个叫做高斯定理 Gauss Theorem。 那对，这个也是这个 Fundamental Theorem of Calculus 的高维度的其他的版本对，后面再说。OK， 那反过来说的话，就是说这个就是用一个式子去把这3个式子写成一个，你不要觉得它太困难就可以了。那 of course, if we need to write out what is the expression of this gradient, okay, we can also write out the gradient is an operator, but we can write it as a different form. So actually, this gradient you can write it as partial x I hat plus partial y j hat plus partial z k hat. Okay, in Cartesian coordinate. Okay, in Cartesian coordinate it look like this. In Cartesian coordinate. Okay, in other coordinate system like spherical coordinate, cylindrical coordinate, the expression will be even more complicated. But this one is in Cartesian coordinate. 然后它是我刚才说它是一个 operator， 它是一个运算的运算的运算的一个符号啊。那所以的话，你看到这个是偏微分嘛？这个是偏微分啊。平常我们写 d 啊，但是偏微分的时候是写这个我们好像叫 run x 这样啊。反正这是一个偏微分的动作。那它这边没有东西啊，所以这个运算符它没有作用于其他东西的时候，它就是告诉你说后面跟着一个什么东西，它就会写进来这个地方啊，写进来这个地方啊。对于某一个东西作用的话，它就会写进这个地方。就比如说这边是这样的啊。那 gradient v 的话其实是 partial x v 然后 I hat， 然后加上 partial v partial y j hat and then partial v partial z k hat 就像这样。所以你看到就是这个就会变成这个就会变成负的 ex 嘛，所以最终的话，它就会整个变成负的1的向量啊，就会大概是这个意思。那这个是这个 operator 自己在这个直角坐标系的表达方式。那这个如果作用于某个东西的话，它就会长这样。因为通常我们学 operator 的话，它们是两个的，比如说1加1、1加2啊，加法前面有一个数，后面有一个数，乘法a 乘 b 有2个数。但是我们也学过一些只有一个运算子的运算符，比如说 cosine， 它就是只有一个运算子的运算符，或者是阶乘也是一个只有一个运算子的运算符。就比如说3阶乘，你给它一个3，它就能算出一个结果，或者是 cosine， 你给它一个角度，它就能算出一个数值出来。那这个的话，这个 operator 就比较复杂的话，就是它算的是一个 field 它输入是一个 field 这里是一个 field， 是一个 scalar 一定是一个 scalar field， 它一定要一个 scalar field 才能放进来这个 gradient 这个地方。然后算出来的结果，它会变成一个向量这个是它一个比较特别的地方比较特别的地方。Okay, so let me stop here. So for this page, because I don't want to talk too much, we just go to a sample problem so that to see how we can apply this. Okay, so this sample problem is like the electric potential at any point on the central axis of a uniform charge. This is given by this. Okay, we just derived this equation in the 2 slides before. Okay, so starting with this, or maybe 3 or 4 slides before. Okay, so starting with this expression, derive an expression for the electric field at any point on the axis of the disk. Okay, so with this expression, and then by making use of this formula, okay, we may be able to get the EX or EZ. Okay, it should be EZ. Okay, because this is a function of Z. Okay, it's not a function of X and Y. So in that case, if you really need to calculate a partial V partial X, okay, so this thing is independent of X, so it is nothing but 0. Okay, because it regards the partial derivative means you only consider x is a variable and then consider all the other variable to be constant 就是偏微分的意思，就是说这个函数它可能有多个变量在那边，所以我们需要用偏微分这个符号。那偏微分这个符号就是说我只对其中一个 变量去做偏导数，那做偏导数的时候，就只看这个是变量，其他的变量我都当做常量来看，常量一导数它就变成0了，如果它是单独出现的话。那所以的话，这个整个是一个对于 x 来说，整个是一个大的常数一导数一偏导数就变成0类似的 partial v、partial y 也是0，但是 partial v、partial z 就不是，所以 so we have a ex to be negative partial v、partial x, okay, and then we can put down this sorry, I mean this one should be z, this one should be z. Okay, and then we can put down this expression sigma over 2 epsilon naught, and then times square root of the z square plus r square minus z. Okay, so this one is a constant. We can just put it outside minus sigma to epsilon naught. Okay, so we take the derivative to the first one. So for the first one, this is the z square plus r square to the 1/2 power. Okay, so take the derivative of it, becomes 1 over square root of the z square plus r square. And don't forget the chain rule, okay, because this is not a pure function of, this is not a pure z, okay, it is also a function of z, so we need to use the chain rule. So we need to take the derivative of the interior function, so it becomes 2z, okay. So this is a chain rule, and then the minus, okay, so this one is negative z, taking the derivative becomes -1, okay, so easy. And then, okay, and then we just need to, sorry, we still have a 2 here, okay, because it is a 1/2 power, we also need to multiply 1/2 in the front. Okay, so in this case, we can cancel this 2 and this 2. And finally, we just distribute this negative sign inside, so it becomes sigma over 2 epsilon naught, and then we have 1 minus z over square root of c square plus r square. So this is the expression for the E view. And okay, this one appear again, okay, for the 3rd or 4th times. Okay, so in chapter 22, we try to compute the E field on the z-axis directly by integration to the E field. Okay, so we get this expression. And in this chapter, what we are doing is we try to get the expression for the potential on this axis first, and then we try to take the derivative, of course with a minus sign, to become the E field, and then with exactly the same expression. Okay, so you can simply compare the steps for calculating this, this V, and using the integration for the E field in chapter 22. Yeah, if you still remember, it should be easier for calculating this one, okay? And then taking the derivative should be easy, should usually be easy when comparing to calculating an integration. 就是去求导数一般都会比求积分来的简单，所以为什么24章要讲一个 potential， 就是它是一个工具，我算 v， 它积分起来比较简单，因为它是一个存量长。我求的它的 expression 之后，我再求一个导数是比较轻松的，比起这个积分直接积分这个 E field 比较困难，所以它是另外一种方式去让你能够求出这个 E field 的。Okay, so let's have a 15 minutes